99.99% server uptime, yet users see service unavailable. The SLI measured the wrong thing, server health, not user experience. That's the classic SLO trap. Let's break down why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover SLO SLA explained. SLI measures what actually happens: latency, availability, error rate. SLO sets the target threshold. SLA is the legal contract with penalties. Error budget is your permission to deploy. An SLI is a raw measurement of your service's behavior. It must be quantifiable and aligned with what users perceive. Typical SLIs include latency percentiles, error rates, and availability. This PromQL query calculates the 99th percentile latency over the last 5 minutes. It tells you the response time that 99% of requests are faster than. An SLO is the target you set for your SLI. It drives engineering decisions. If the SLO is at risk, you stop shipping features and fix stability. The time window matters: 30 days smooth spikes. This YAML defines an SLO. 99.9% of requests should have latency under 300 ms over a rolling 30-day window. It's a config file that codifies your reliability target. An SLA is a legal contract between you and your customer. Unlike SLOs, which are internal, SLAs have consequences. Breach an SLO and you have a post-mortem. Breach an SLA and you write a check. This SLA example shows the contractual terms: availability target, measurement method, penalties, and exclusions. Note that scheduled maintenance is excluded. Define these clearly. Error budget is the amount of unreliability your service is allowed. As long as you haven't exhausted it, you're free to deploy. Once depleted, you stop shipping features until reliability is restored. This Python class calculates remaining error budget. With 99.9% SLO and 10 failures out of 50 requests, you have 80% budget left. It turns reliability into a numeric yes/no. Burn rate tells you in real time how fast you're consuming error budget. A rate of 2 means you'll exhaust it in half the window. Monitor this as a P1 alert threshold. These Prometheus alerting rules fire when burn rate exceeds thresholds. High burn rate is critical. Sustained low burn rate is a warning. They catch both fast failures and slow regressions. A single burn rate window gives false positives. Use 2 windows, short for fast events, long for slow drifts. Alert only when both exceed thresholds, eliminating noise from transient spikes. This Prometheus configuration creates recording rules for burn rates over 1 hour and 6 hours. The alert fires only when both conditions are true, so a single spike won't page you. Never let your SLA match your SLO. Set SLO tighter to provide a buffer. Define exclusions like scheduled maintenance and customer-induced failures. Standard penalty is 15% of monthly fees per 0.1% below SLA. This contract YAML shows the structure. Internal SLO is 99.9%. Contractual SLA is 99.5% with a clear buffer. Exclusions and credit calculations are defined to avoid ambiguity. The mental model is simple. SLI answers, is it working? SLO answers, are we okay? SLA answers, how much do we owe? Don't let marketing or legal define your SLIs. Insist on latency and error rate. This config model shows the hierarchy. Define your SLI first, then set an SLO target, then write the SLA clause. Never start with the SLA. An e-commerce app with separate SLOs for search, checkout, and payment. When payment starts timing out, the burn rate alert fires. Because SLOs are per service, you can fail over the payment provider without taking down the whole site. This configuration defines per service SLOs with different windows and burn rate thresholds. Payment has a critical burn rate of 14, meaning if it spikes, you get alerted fast. SLIs, SLOs, and SLAs are useless without tools to measure them. Platforms like Datadog and New Relic provide ready-made SLI dashboards and error budget tracking. Dedicated tools like Noble9 codify SLOs as code. This Datadog SLO definition monitors P99 latency with a 99% target over 30 days. It automates the math and surfaces warnings before your weekend is ruined. SLOs built in isolation get ignored. Involve stakeholders by asking what success looks like from the user's view. Use error budgets to frame trade-offs. Raising the SLO to 99.99% means fewer features shipped. This proposal shows concrete trade-offs between SLO target and cost. It makes reliability a business decision, not an engineering ultimatum. Setting an SLO at 99.999% sounds heroic, but destroys velocity. Start by measuring current SLIs. Set targets slightly above baseline to drive improvement, but not so high that routine deploys exhaust the budget. This check shows that, with a current SLI of 99.8%, proposing a 99.9% SLO is unrealistic, because the current error rate would exhaust the budget in 5 hours. This is the same issue we highlighted at the start. Here's exactly why that happened. The SLI was defined as server uptime, not user visible availability. The server was up 99.99%, but users experienced errors. The SLO was met on paper, but the SLA was violated because the metric didn't reflect user experience. The fix was to redefine the SLI to measure user-facing request success, not server uptime. Implement synthetic probes or real user monitoring to capture the actual user experience. Now the SLI reflects what customers feel. This was the exact mistake in the incident. The SLI was defined as server uptime. It showed 99.99%, but users saw errors. Always define SLIs based on user-facing metrics, not infrastructure health. Setting an SLO without knowing your current SLI is guessing. You'll either set impossible targets that demoralize the team or trivial ones that don't push improvement. Measure your SLI for at least 2 weeks first. If your SLA matches your SLO, you have no room for error. A minor incident triggers penalties. Always set SLO tighter than SLA, e.g., SLO 99.95%, SLA 99.9%. The article mentions segmenting SLIs by geography or endpoint, but does not emphasize that SLIs should be measured at the granularity of user-facing operations, e.g., login, checkout, rather than infrastructure-level metrics like CPU. This ensures the SLI reflects actual user experience. The article discusses burn rate alerts, but does not show a concrete Prometheus alert rule for error budget remaining. Here is a rule that alerts when less than 20% of the error budget remains, using the slow error budget remaining metric. The article's SLA example includes scheduled maintenance exclusions, but it does not stress that maintenance windows must be clearly defined and communicated to customers in advance. Without this, customers may still claim SLA breaches during planned downtime. When error budget burns faster than expected, check your SLI measurement source. Compare against actual user complaints. Look at high percentiles. Inspect SLA exclusions. Implement synthetic transactions to catch silent failures. Let's run through some common interview questions. What is the difference between SLI, SLO, and SLA? SLI is the data, SLO is the goal, SLA is the promise. How do you decide the right SLO for a new service? Collect SLI data for 2 weeks, consider business impact, set SLO stricter than SLA. Your error budget is depleted. What do you do? Freeze releases, identify root cause, apply fixes, resume when budget recovers. Why is it risky to use a single global SLI? Hides regional or endpoint-level degradation. Segment by geography or user journey. And a few frequently asked questions. Do I need an SLA for every service? Not necessarily. Start with SLI plus SLO, add SLA only for commercial agreements. Can I use the same number for SLO and SLA? Technically yes, but risky. Set SLO stricter to provide a buffer. How often should I review SLOs? At least quarterly, after major outages or infrastructure changes. What window should I use for error budgets? Typically a rolling 30-day window. Some teams use 7 days for faster feedback. To recap, measure what users experience, not what servers report. Set a data-backed target with headroom above your SLA. Only promise what you can measure. Error budget is your permission to deploy. Start small and iterate. Ready to go deeper? Up next, alerting and on-call best practices, then log aggregation best practices, then chaos engineering basics. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.